Hi, and welcome to this week's episode of the Structural Engineering Podcast with Max and Zach. This week we're talking with Jon Schmidt, a structural engineer with Burns and McDonnell, about blast design and the loads of which are applied to structures. Max and I really enjoyed speaking with Jon and hope to discuss different topics in the future. Let's jump in.
I'm Jon Schmidt. I'm a senior associate structural engineer with Burns and McDonnell in Kansas City, Missouri, and I'm in the aviation and federal group where I specialize in the design of military administrative buildings. And when September 11th happened, I happened to be in a situation where I had some time on my hands, so I did a bunch of self-study on blast design, anticipating that anti-terrorism is probably going to become a thing in our profession in the foreseeable future. And sure enough, that's what happened. It wasn't much later that the Department of Defense came out with its first version of its minimum anti-terrorism standards for buildings. And so I was able essentially to position myself as my firm's specialist in that area, and then also got involved with various industry organizations and committees and so forth on anti-terrorism and blast design. So that's what's led me to where we are today, and presumably why you're talking to me about this topic.
What point were you in your career when you decided to do this self-study? Was this earlier on? I guess 9/11 is,
I was about 7.5 years into my career. So okay. I had a PE at that point and was doing structural design where I was responsible for projects. Mm-hmm. But again, I just happened to be in a lull when I didn't have a lot of billable work on my plate at that time, and got permission from my management to spend that time digging up all the resources. And that was almost the hardest part of it, was finding the information, because especially back then, a lot of it was controlled and difficult to get without a clearance, or at least for official use only and things like that. So just being able to dig through and get the information. And then I kind of made it a personal mission to help the profession as a whole get a little more up to speed. So I wrote a lot of articles. I gave a lot of presentations on simplified blast effects analysis and design, the kind of stuff that a quote unquote ordinary structural engineer ought to be able to do. And that's still kind of the level where I am now, almost 20 years later, admittedly, but that's because that's the type of work that I've done for these Department of Defense projects. Typically, it's a relatively small explosive at a relatively large distance on the outside of a building, so that the blast effects can be modeled in a relatively simplified way as compared to other scenarios where you've either got a very large explosive, or it's very close to the structural element, or it's inside. So when you're inside in a confined space, all those surfaces tend to reflect the blast shock waves and magnify the effects considerably on every one of those surfaces. That gets a lot more complicated, and so I tend to stay away from that. Those are situations, and there are a few others, where I like to call in what I call a super expert, somebody who was doing blast design before 9/11 and therefore is at a much higher level of specialization than even I am at this point.
I did watch some webinars before this and saw some of the very impressive modeling of enclosed spaces and blast pressures moving through hallways, moving through equipment, how it magnifies around things. It seems like the end level of complication of this is very, very high. Well, I shoot for ordinary person.
Yeah,
so.
Again, in a real specialized situation, you can even do similar type of modeling for an urban environment where it's outside, but you have a lot of surfaces nearby that are going to be reflecting, focusing, deflecting, whatever. The blast wave is not just a nice hemisphere, which is what the simplified methods that I use assume. It's a hemisphere of explosive placed on the ground that propagates as a hemisphere as well. And it's far enough away that you can simulate it as if it were applying a uniform pressure and impulse to the entire surface of the element that you're checking.
I found a video that was discussing blast design in an urban environment. I believe it was in New York, and I would never have thought how much the blast reflected off the buildings. My mind was blown. It opened my mind up to so many different things of how the whole design works.
Yeah, even as it's shattering all the glass, it's still reflecting off that, and it affects further away than what the magnitude of the loads are on other structures.
Let's backtrack a second and starting from the very, very beginning. Could you explain to us what is blast design? Like, when we're analyzing a structure for blast, what are the goals? Like, what is the expectation of a building that has been designed for blast, and what really is the loads that we're looking at? I'm sure there's a lot to unpack in there.
Sure. Well, the first step anytime you're going to do blast design is to figure out exactly what you just described, which are the design criteria for this particular structure in this particular location for this particular client. And so there's two different scenarios then. In some cases, there's some sort of prescriptive standard that tells you this is the scenario for which you have to design this. And that's a lot of the DoD work that I've done. They say this is the charge weight and your minimum standoff distance is this. And if you're less than that, then you have to do the explicit blast analysis. And if you're farther away than that, you actually just can do conventional construction. That's how DoD projects used to work. They've actually backed off on their requirements in the last few years so that there's less blast design to be done for DoD projects now than even just 5 years ago. But if you don't have somebody prescribing for you what those criteria are, then you have to do a risk assessment. And what you're doing then is you're evaluating three factors: consequence, threat, and vulnerability. The consequence is really the magnitude of the bad stuff that would happen if a building or other structure were to be damaged by an explosion. So if you're working on a small building with only 3 or 4 people in it, the consequences are much smaller than if it's a multi-story building with 1,000 people in it, and things like that. Sometimes, and again, in the DoD world and a lot of even in the commercial world, typically consequence is measured by the number of people who could potentially be injured or killed by the after effects of an explosion. There are other situations, though, again, especially government agencies where they're worried about infrastructure. Maybe they're worried about high value equipment. They're worried about the mission that's being carried out in a particular facility that they don't want interrupted in any way. And so all of those factors have to go into some sort of at least nominally rational process in order to figure out two things. First of all, on the load side, what is the design basis threat? What is the size of the explosive that we're going to assume for our design? And also, what is the location of that explosive? And more to the point, what is its distance from your structure that you're designing? So that's the demand side of the equation. The capacity side, the resistance side, is what is the level of protection that this facility needs to provide to its occupants or to whatever else is inside or associated with the structure. So the consequence piece of that risk assessment tends to give you that level of protection that your design has to provide. And so that establishes what are your resistance criteria. And then the threat assessment is what gives you the design basis threat, which is the load side and how big an explosion, how far away, and things like that.
For that resistance criteria, is the target collapse prevention generally, or is it looked at in that sense where it is,
Yeah, there are different levels, sort of like in performance-based seismic design now. You've got those different levels of performance that you can use as your target. It's the same thing really in blast design. So if you have a relatively inconsequential scenario where, if that building falls down, it's a bad thing, but it's not a horrible thing. So you might be in a very low level of protection where you're actually allowing damage right up to the threshold of collapse for the design basis threat. You go from there up to a low level of protection, which is that it's damaged and it's unrepairable, but it's not close to collapsing. It's still going to be intact and you can at least get people out of the building and protect most of the property and so forth. The medium level of protection then is repairable damage. So you're assuming that you're going to be able to go in after the explosion, fix things up, and still continue to use the building rather than in the lower levels potentially having to tear it down and start over. And then the high level of protection is where you want this building to keep running almost without a bump if this event were to happen. So again, very similar to like our risk categories in ordinary structural design, and then especially the performance-based design where you have those explicit objectives.
I keep cutting Zach off here. He's got a question, I know, but I've got one in between. That is, I assume the clients here are generally very informed about what they want. They're coming to you with, we want this product against this blast. And maybe there's a conversation there, but they know what they're looking for. Is that right?
You would think that, but Unfortunately, in a lot of cases, it doesn't quite work that way, even with our military clients in the Department of Defense, because we're typically working with people who are on a base, who are carrying out a military mission. They don't design or construct buildings for a living, so they don't really have any idea what it means to say, oh, you've got to design this building for 500 pounds that's 10 feet away, which is a really big deal from a blast design standpoint. And so we typically do have to do some education with a lot of our clients, even again in the DoD world, and make sure they understand here's the process. And DoD, actually, the installation is who does that risk assessment for us on projects where, for whatever reason, someone has determined that just meeting the minimum standards is not sufficient. So recently did a project for a large operations center type facility, and their executive officer said, we're designing risk category 4 for all the normal structural stuff because this building can't be interrupted by anything, including a terrorist attack. And so the installation then went and did the assessment and gave us the design basis threat and the level of protection that we had to use for our design. But there was still an education process then, and to a certain degree, we were helping bridge the gap between the anti-terrorism people on the base who knew exactly what they were talking about and what the requirements were, and the ordinary officers and enlisted folks who are going to be in the building eventually, so that they understood what the ramifications were, not only for the design and construction, but for the cost, and then for some of their operational procedures and things like that.
What is an explosion, and I guess what characteristics does a blast wave have?
Well, I'll read you the definition of an explosion from ASCE's Standard 59, which is blast protection of buildings. I've had the privilege of serving as the vice chair of the committee that wrote that standard, and a new version is just about ready to be published. We just had the public ballot. We've got one minor comment, which I actually made, that needs to be resolved. But it should be coming out hopefully by the end of the year, and if not, early next year. But anyway, the definition of an explosion there is a rapid chemical reaction that produces noise, heat, and violent expansion of gases. So that doesn't tell you much from a structural engineering standpoint, but that is, at least in the vernacular, what an explosion is. And then the definition of an explosive is a material or device that is capable of causing an explosion under certain conditions, such as heat, shock, or friction. But then you also have to drill down. There are all different kinds of explosions. So if you look at a different ASCE publication on design of blast-resistant buildings in petrochemical facilities, it talks about vapor cloud explosions, pressure vessel explosions, condensed phase explosions, which are your more the intentional high explosives, and dust explosions. So you've got all these different varieties of explosives and explosions that are potentially going to affect a building. And that also feeds into then the risk assessment and the design criteria that ultimately we rely on the clients to help us figure out. If you're doing a project at a petrochemical facility and all they're worried about is an accidental explosion, then it's probably going to be a deflagration or a vapor cloud explosion, something along those lines. And those tend to have relatively low pressures but long durations. What I'm used to doing with the DoD world, where we're worried about terrorist attacks, is a high explosion. And so the main difference between an explosive loading or blast loading and what we're used to doing on a daily basis in structural engineering is that it does have a very high magnitude and a very short duration. So the magnitude is typically in pounds per square inch, 5, 10, sometimes 20, 30 pounds per square inch, not per square foot. But the duration is also very short, measured in milliseconds, sometimes as short as 10 or 15 or 20 milliseconds. Again, for those petrochemical type explosions, it might be a few hundred milliseconds, but it's still less than a second that load is applied. And so the upshot of that is it's really tricky to try to convert that into some sort of an equivalent static loading like we do even for earthquakes. Earthquakes, of course, are a highly dynamic loading with a high magnitude and a short duration, but there are also multiple cycles of it over a number of seconds, not milliseconds. And so it lends itself more easily by just assuming certain levels of ductility, which is where we get our R factors for different structural systems, to have a prescriptive static loading for a given ground motion and a given structural system. Blast doesn't work that way. You have to check each individual member individually to figure out what would be an appropriate equivalent static loading to represent the blast. And there are some closed form equations out there for a couple of different ways to model it. If you treat it as if it were an instantaneous impulse with zero duration, there's a closed form equation that will tell you what the deformation of the member will be relative to its yield deformation. And so you can take a look then at the ductility of the member based on that. And then on the other end of the thing, there's a quasi-static loading, which again is more applicable maybe to those deflagrations where it's applied suddenly and never removed. In between those two, Nathan Newmark, pretty brilliant guy and well known in the seismic world, came up with an empirical equation that combines those two closed form solutions. And so that really is the most common simplified method of doing blast design of an individual structural member. You use that equation to come up with an equivalent static loading that is uniformly applied to the member, and then you check the maximum deformation against a response limit. Now, those response limits are putting us back on the resistance side, and that's where the level of protection comes in. You'll find tables in the standard for different response limits for different structural materials in different applications, like flexure versus shear versus axial loading and things like that, that will give you response limits for those different levels of protection. And then those response limits typically for a ductile material like steel are the ductility ratio. So you divide the maximum deformation by the yield deformation, and that parameter is what you check to make sure that you're okay for a certain level of damage that is anticipated. For more brittle materials like concrete and masonry, a lot of times it's actually just the idealized end rotation. So that maximum deflection, you treat it as if that were a plastic hinge at that location, straight segments between those and the supports, and you have a limit on the rotation at the support. So it's a couple of different ways that it gets measured, but the bottom line is it's a dynamic analysis that can be translated into a static analysis, but only on a member by member basis based on the span length, the size of the member, the end conditions, and those response limits that are dictated by the level of protection.
I'm curious on material-wise. I can't imagine many military or DoD installations that are made out of wood. So it sounds like, are you typically seeing concrete and steel mainly as building materials, or is there one that kind of outshines the other when looking at blast design?
Not really. I mean, military doesn't use wood for buildings in general, so we don't run into that. There are response limits in the ASCE standard and out there in the literature for wood construction, so it can be done. Cold form steel as well, and there's been a lot of research done in the last 15 years or so on cold form steel stud wall behavior under blast loading and development of some special top and bottom connection details, because that tends to be where cold form steel fails, is it shears off at the connections rather than it being a flexural ductile failure. But masonry, you'd be surprised, reinforced masonry is actually a very good material for blast resistance. And the reason why masonry as well as concrete are good is because mass, although it's detrimental for seismic design, is actually beneficial for blast design, because mass provides inertial resistance to that very short duration, very high magnitude loading that is applied by the shock wave from an explosion as it passes over the face of the structure. And so masonry, being a very massive material, is helpful from that regard, as long as it's reinforced properly, of course, so that you also then are able to get the ductility that you need to develop some inelastic response.
Man, I think you're breaking Zach's heart. He's wood's #1 fan. He's got posters of pieces of lumber. He's got everything.
Last time I checked, wood burns. So yeah, in an explosion, it's maybe not the best.
Now Zach has it. He won't even burn it.
It doesn't burn. It's perfect. It's the best material out there. I did see some blast loading. There's some testing for CLT, cross-laminated timber, and that looked pretty cool. But
yeah, I would be surprised, and I'm sure the wood industry is continuing to do research, just like the cold form steel folks have done, to try to make their material more competitive in those situations.
So we're talking about blast as pressure as the primary thing. What are the other effects? You mentioned, in the definition of explosion, we've got light and noise, and are there other components that we need to design for? Like, does heat come into play at all when looking at the structure? Does debris, is that part of this always, or is that like a different addition?
Good question. Yeah, the the primary effect that we typically use for blast design, particularly again in the simplified situations that I do all the time, is air blast. So it's a shock wave that propagates, and we idealize it as a perfect hemisphere. And again, the explosion is far enough away that by the time it reaches your structure, it can be simulated as if it were a uniformly distributed load over that tributary area for that short duration. And but there are other effects that sometimes need to be taken into account. That's another case where I usually say that's when you need to call in a super expert, when those types of other effects are significant. So you mentioned one, which is debris, and there's really two types of fragments that we are concerned about in some cases. Primary fragments are the actual casing on the explosive. Those generally are only a consideration when you're assuming it's very close to your structure, and so you're actually going to have those shards propelled into your tributary area. But the other are secondary debris, where you've got stuff that's in between the explosive location and your structure that gets picked up by the shock wave and thrown at your building. Mm-hmm. And so that can be a concern in certain situations, particularly if your risk assessment tells you that you can't have any penetration of that exterior wall for one reason or another, because that's what's going to happen with the fragments. It's usually not going to be a problem with the structural response, the inelastic response and all that. It's more what your surface material is and it getting perforated, penetrated by those secondary fragments that get picked up and thrown at it. Another one that sometimes comes into play is ground shock. If there's a bomb on the ground and it explodes, what's going to be there afterwards? A big crater. And so that sends seismic waves essentially through the ground that can impinge on an underground structure. So if you've got a basement, or if you're looking at a bunker or something that actually is below ground, then that becomes a design consideration. It's typically not something we need to worry about just for the foundations of a building. But again, hopefully a risk assessment would identify any unusual situations where that does need to be taken into account. Another one where fragments are an issue, a project I was involved in about 10 years ago, is when you're doing a fuel tank. And so you're not so much worried about a structural failure of the tank, but you're worried about fragments punching holes in the tank and all the oil and fuel leaking out. And so, again, that's a situation where we had a subconsultant who was a blast specialist and was able to do the right kind of fragmentation modeling to give us an idea of how far away our design basis threat needed to be so that we could put the fence and the barriers and whatever else at that distance to make sure that that wasn't going to be a scenario. But again, you're always operating under the uncertainty that, well, we've designed for 1,000 pounds. The terrorist doesn't know that, and darn it, he might use 2,000 pounds. And the other joke I like to tell about windows, and maybe we'll talk more about glazing later, is if you've got operable windows, then just make sure whenever you open them that you put out the no terrorist attacks allowed sign.
Blast design, fragments. Is there anything like tornadoes where we have like prescriptive assemblies? With tornado design, you say like, oh, if you masonry and you fill it with grout and whatever. Is there any component that is similar there for design against fragments, or is it you start from scratch?
Yeah, not to my knowledge. And if you look at the ASCE standard, there's a chapter on fragmentation, but the prescriptive part's very short, and there's a bunch of stuff in the appendix because that's one of the least well understood phenomena in blast design. So there are several different models out there, several different methods for designing for fragmentation, and the industry really hasn't reached full consensus yet on what the best approach is or the most successful approach for accommodating those fragments. But there are test standards for doing blast testing of assemblies, particularly again for glazing, although they can also be used for other types of assembly. And so you can test them, but you're testing them for, again, an explosion, and it's air blast that is the primary effect of that in an arena or even in a shock tube. It's very difficult, obviously, to simulate fragmentation because what you throw out there to be picked up and hurled at the building by the test may not be what's out there in the real structure.
All right. So 20 years ago, you kind of dove into blast design and trying to understand all these items. If I were a new engineer sitting down to do a building with blast design considerations, where would I start with code? Is there a federal code I start with? You brought up ASC 59. What does that look like code-wise?
Yeah, nowadays I would probably start with ASCE 59. I would wait until the new version comes out first, but there aren't any major changes. We just did some tweaking and some updating, and the fragmentation chapter has been beefed up a little bit with some new research and things like that. But I think that's a good place to start. There is a handbook for blast design that several of the folks involved in preparing the standard wrote when it first came out back in 2011. I don't have the title at the tip of my tongue, but Dusenberry, I think, is the lead author. So that would be something to look for. Again, if you're doing petrochemical design, then the ASCE guide for that is a good resource. If you're doing more protective design against terrorist attacks, there's a brand new ASCE manual of practice that just came out in the last couple of months on structural design for physical security. So those are all good. They're not necessarily introductory texts, but they're definitely good resources. What I would probably suggest you do is go on Structure Magazine's website, www.structuremag.org, I believe, and find some articles that I and others have written over the years that are at more of an introductory level and will point you towards those and other resources for diving a bit deeper.
Would you say it is something, so if you were approached by a client and asked if you could, not you, actually, let's say if I was, is it something that you can get into, with your traditional structural engineering understanding, could you do the research and be prepared to do a project in a reasonable amount of time if you didn't have someone in the firm that has done this before?
I think it can be done. I mean, essentially that's what I did, right?
Yeah.
So it can be done, but you have to have a lot of time and a lot of patience and management that's willing to let you do that, or a client who's willing to pay you to do that, to delve into that far. It's certainly helpful if there's somebody in the firm who has some background and at least can answer questions as they come up. I'm a big believer that there are no dumb questions in engineering. If you don't know, it's better to ask now and find out, and don't worry about thinking, I'm going to look dumb if I ask this question.
Yeah.
No, we want you to ask because we'd rather you not get too far down the road and find out that, I wasted the last 2 weeks doing it this way when I should have been doing it that way if I'd only asked the question at the time. So, like anything else that's not in the curriculum, not going to get tested on a PE exam or an SE exam, you can get there, but it takes time, it takes study, it takes effort, and it really ultimately you just have to kind of roll up your sleeves and start doing it, and hopefully again have somebody who has done it before and can look over your shoulder and point you in the right direction.
Excellent. I guess I'll throw in my own caveat there is like you can always also have someone else review the project outside of your firm, pay a subconsultant to look at your design, which is, what a lot of people do. If you're, say, an East Coast firm trying a seismic design, you could have someone review it. So throwing that in for myself, if someone did come, you could probably learn there. But if you don't have someone to review it, you can go out and find somebody else.
And again, I really felt strongly and still do that it's important that ordinary structural engineers be aware of this and have some knowledge and capability, at least with the same kinds of simplified methods that I have been using, I've been talking about here so far. And there are resources out there to help you get there, including seminars and webinars and things that I've done over the years.
Mm-hmm. So talking to bridge engineers in the past, they've mentioned before, it takes time to load a structure. The speed of a vehicle over a bridge will load it differently at different speed increments. How does that relate to a building with blast? If it's so quick, how does the building actually have time to get loaded during that event?
Sure. Well, typically we're not analyzing the entire building and its response. So if you look in the petrochemical guide that ASCE has, there is some discussion about base shear for a blast, but that's again because in petrochemical situations, you usually have a lower pressure but a longer duration of loading so that it's closer to a quasi-static scenario. And so there is load on the building for a longer period of time that can mobilize that entire load path. With what I do with high explosives, short duration, high magnitude, we really just look at an individual structural element. So, for example, if you have a stud in a wall or a masonry wall, a strip of that wall, and you come up with this uniformly distributed load with its millisecond duration and several psi magnitude, you do your analysis of that, and you just make sure that you meet your response limits. So the ductility ratio and or the support rotation are within those limits that we talked about earlier. But then for the connections, you just make sure that the connections are adequate for developing the full dynamic moment capacity of the member, because flexure does tend to be the dominant response mode in these short duration, high magnitude load situations. So you're not actually transferring that same whole blast loading all the way down the load path, because when you are having inelastic deformation, essentially the assumption is you're absorbing the energy that the blast is imparting to the structure with that inelastic deformation of the structural element itself. And again, as long as the connections don't fail while that's happening over a few milliseconds, you're not going to transfer much down the load path. So you're not looking, again, in summary, over the entire building. You're not assuming that it is mobilizing the whole structure all at once. You're looking at it one element at a time. And there is some simplification, again, and idealization there in terms of not coupling the dynamic response. So, for example, if you have roof joists sitting on a girder, they're both going to respond, and they're going to respond in a way that ties together somehow. And if you're really worried about it, there are methods of multi-degree of freedom analysis where you can look at it more rigorously that way. But the fact of the matter is, in most cases, again, especially with DoD type scenarios, the charge weight and standoff distance are such that it's a reasonable simplification to look at each component individually.
When you're designing connections to have this added ductility, how much different do they look than your typical, let's say you had a wide flange connection with shear tabs? Once you go through the analysis, does the required connection size look dramatically different? Are these like every beam is kind of full pen moment connection, or even beefed up more than that, reinforced somehow? Or is it looks similar to what you might expect a traditional building?
Yeah, for blast design, you typically, the connections, you start with whatever your normal shear connection would be, and you check it, and a lot of times it's fine. You might have to add a bolt in a shear tab, or a row of bolts in a double angle, or what have you. But the fact, again, that you're really just making sure that the member won't fail in shear before it starts yielding in flexure, and you can't apply any more load to the connection in terms of the load path than what would develop that dynamic moment capacity. And I should mention, dynamic moment capacity is a magnified value. So it's not just your phi m sub n that you would calculate using the code. First of all, we typically do not apply resistance factors in blast design because we're trying to estimate the actual yield point of the member, not provide a factor of safety to prevent that from happening. So number one, we don't apply by a phi factor that's less than 1. And in fact, we actually multiply the resistance by a number greater than 1. Typically, we add about 10% just under the assumption that the actual strength is going to be about that much higher than the specified minimum strength. So if you have 50 KSI steel, hopefully all your steel is going to be stronger than that. And studies have shown the average is about 10%, so 55 KSI. And then you also apply another factor that's usually greater than 1 to represent, again, the fact that this load is applied in a very short duration. And because of that, there's an inherent increase in the capacity of that member for that short duration load. It's called a dynamic increase factor to take that into account. So typically for a steel member, it's 1.1 for the static strength, and then it's something like 1.19 for the dynamic strength. So you end up increasing your assumed strength by about 30%, and that's the value that you use as your yield strength, and then you do check all your ductility ratio and your deflection and your connection capacity for that value.
Interesting. So that increase of 1.1, that sounds exactly like an ROI in seismic design, right?
Yeah, very similar. Same
delivering
idea.
as much as possible. Huh. Cool.
What I will mention, since you brought up seismic, and I think one of the questions you had sent me ahead of time was, is it just a lot like seismic to do blast design? And the answer is yes and no. It's yes in terms of the detailing a lot of times, in terms of trying to develop ductility in your members, whether they're steel, concrete, masonry, whatever. But no, in the sense, like I mentioned earlier, an earthquake loading is cyclic, and you go through multiple cycles of the whole building shaking all at once in each direction. As well as vertically in some cases, whereas Blast loading is very highly localized. So again, we're only checking one member at a time, and it's only applied once and then it's gone. So you get this big hit in a few milliseconds, but then nothing else beyond that. So the loading is very different from seismic, but a lot of the detailing principles end up being similar simply because in both cases you're trying to ensure that you have ductility in your members and connections.
When I was, before we started recording, I was thinking about that question, actually. I'm thinking that it might be a little closer to tornado design, if anything, but sounds like it's not even really that close to that either.
Because again, even for tornadoes, a lot of times we're converting to a static load that based on a wind speed as a sustained load over time. And so, it's very different from that standpoint.
When would you analyze a structure just for blast design, and when is collapse prevention analysis used?
Nothing comes to mind of a situation where the only thing you would design a structure for is blast. Obviously, you're going to still have to check for all your code minimum loads for dead, live, snow, wind, earthquake, and so forth. There are situations where blast is obviously the controlling load case. And so again, a lot of times though, for building design where again, it's a reasonable size explosion at a reasonable distance, you design everything for your standard code loads and then you check it against blast and then beef it up where you need to, rather than starting with blast. Generally, we don't start with blast as the very first thing that we check because we might end up with something that is already too little anyway. The blast might not be the controlling, or again, doing what we need to do gets us where we need to be, and so the blast ends up being a box that we can check at the end. Now, collapse prevention is a different question, and I did want to talk about that because there is this issue of, well, when do you worry about progressive collapse in particular? And the industry standard, the way it has gone is that if you have a one-story building or even a two-story building, generally you're not worried about progressive collapse because you only have those two levels. But once you get to 3 stories and above, that's where the federal government, including the Department of Defense, requires you to design to resist progressive collapse, and where, if you were in a private sector situation, I'd probably be recommending to an owner who's worried about this kind of stuff that they consider designing for progressive collapse. However, the thing about progressive collapse design is that for the most part, it tends to be threat independent. So you're not actually designing a building against blast when you design it to resist progressive collapse. You're designing it against the removal of a column for any reason whatsoever. So it could be a vehicle crashing into the building. It could be an explosion. It could be any of a number of other things, somebody firing a shoulder-fired weapon at it from a distance if you're in an environment where that happens. So, but the point is that you make some simplifying assumptions. You pretend that column just magically disappears, and then you make sure that the building doesn't fall down just because that one column is missing. And that is a case where you would see very different connections for your beams because they now have to have moment continuity through every connection to a column in case the one right below disappears. So you end up with moment connections all around the perimeter of the building in order to hold the building up. DoD does have an alternative approach that's more prescriptive, where you don't have to do an explicit analysis for removing a columns, and what you do instead is you put a lot of extra rebar into the floor slabs and also the roof slab, and they do have to be concrete to use this provision. And so they call this the tie forces method, and the theory behind it is that all that extra reinforcement provides tensile capacity so that a slab or a beam on the perimeter would go into catenary action if a column were removed and transfer all of the loads back into the undamaged portion of the structure. Now, there have been some studies questioning whether that's really how a building would behave in that scenario, but for certain types of buildings, it is a more cost-effective way to meet the minimum progressive collapse design requirements rather than having to design every beam around the perimeter to span over a column that's missing.
So I was just thinking off the top of my head, like if I were to drive around, I think it's very easy to think of maybe certain structures that would be blatantly designed for blast. But could you kind of describe what structures you'd see designed for maybe a different level of blast or ones that might not? Obviously, you can't go into probably the ones you've designed, but a federal building versus something on a base versus something that's in a foreign country.
Yeah, I mean, I think embassies are probably one of the most obvious examples where you can tell that they were worried about it and took it into consideration, because the Department of State's requirements are much more rigorous, particularly in certain countries, as you can imagine. Afghanistan just comes to mind for some reason. But the issue is you usually end up with few or no windows or very small windows and very robust reinforced concrete construction. You won't see a lot of glass on the facade. A lot of times you won't see steel framing. Certainly won't see cold form or masonry or wood. Sorry. So that again is the most obvious one that comes to mind. I think older federal buildings, when I say older, I mean, 90s, when they started designing after the Murrah building incident in 1995. I think, they started beefing up federal buildings to be a little more robust, but over the last 10 years now, again, I think the industry's advanced to a point where if you look at new courthouses, for example, that are being designed and constructed around the country now, there's a lot of glass. They look very normal, like an ordinary administrative office building, and so they're able to, in essence, hide the blast resistant aspects of it, in part because they also have bollards all over the place around the perimeter of the site to keep the explosives at a reasonable distance, the larger ones anyway. That actually brings up something I could talk about going back to the criteria development. You look at different magnitudes of explosives. So if you're worried about a vehicle bomb, then what you're going to be concerned with is how big a vehicle can actually get close to my building. Where's the parking lot? Are there any bollards or barriers that would enforce standoff distances if someone was determined to ram the building in a suicide type attack? Are you on an installation where they actually have the capability to search vehicles before they get anywhere near your building? That allows you to use typically a smaller design basis threat for that scenario, because you've got an operational mechanism for limiting the size of explosive that can get there. If you're worried then about something getting closer, now you're talking about a suitcase bomb, briefcase bomb, maybe a roller bag, that size of explosive that somebody could hand carry, just kind of leave it somewhere and let it go off. When you start looking at getting into the interior of the building, like lobbies and things, anywhere that's before a security checkpoint with x-ray machines or scanners or what have you, especially if you've got columns in that lobby where you could set something right up against it, that's a lot of times would trigger a requirement to do progressive collapse design and things like that. So, and then the third type is a standoff weapon, what they call, where there's no way you can actually prevent it from hitting the building because it can be fired from a distance, like a shoulder-fired weapon that I mentioned earlier, like a mortar, where you're lobbing an explosive of some type over whatever protective measures might be in between, and then it can land on the building. And so for that scenario, one of the things you can do is have a sacrificial roof structure, so maybe it's cold form steel trusses or something like that, with a concrete slab underneath them so that the weapon detonates when it hits the standing seam roof, but you get at least a few feet of standoff distance before you're impinging the actual structure. And you'd be surprised at how much a few feet of standoff can do, particularly against the smaller size of explosive that could be fired at a building from a distance like that.
I like that. That sounds sneaky. Just a fake roof.
The other one that I have in slides that I present is a pre-detonation screen, where you have a screen so that if somebody fires a weapon, it'll detonate at that screen and then just kind of bounce off the building because it's already. But as I always say, architects aren't big fans of pre-detonation screens because they're incredibly ugly.
Oh yeah, mosquito net the whole building. Just stand it off 20 feet.
Net wouldn't do it. We're talking a fairly robust structure that ends up being a wall, and nobody gets to see the building.
Yeah. I guess with those different size blasts, is there, I'm probably oversimplifying this, but like that pressure you get, that high PSI, is that per pound of that you can sneak? So like you might say like a briefcase bomb might hold 20 pounds of TNT equivalent or whatever, and that equals 5 PSI.
Great question. I probably should have covered that earlier. The standard equation that's used for calculating blast effects on a structure is based on TNT as the default explosive. And if for whatever reason you've got a different type of explosive that is your specific design basis threat, like C4 or ammonium nitrate and fuel oil, like Timothy McVeigh used in Oklahoma City, there are tables for converting the weight of that different explosive into an equivalent weight of TNT. And so ANFO, ammonium nitrate and fuel oil, is a less energetic material, and so its factors are less than 1, whereas composition C4 is a more energetic material than TNT, so its coefficients are larger than 1. But in any case, you convert the weight of whatever material that you have into an equivalent weight of TNT. And then the parameter that really matters for figuring out all the other aspects of a blast loading is what they call scaled distance. And so what that is it's the actual distance divided by the cube root of the TNT equivalent weight of the explosion. And why it's the cube root is because the energy that's imparted by a shock wave is proportional to the cube of the distance, because again, it's a hemisphere. So it's the surface area of that hemisphere that is proportional to the magnitude of the punch that shock wave is going to deliver to any surface that gets in the way. So standoff distance really is the most cost-effective way to mitigate blast. The farther away you can get your assumed explosive of whatever magnitude from your building, the less severe by that factor of cubed are going to be your pressure and your impulse. Those are the two parameters that you get from the empirical equations that are standard in the industry. So again, the pressure is an almost instantaneous shock wave pressure that is suddenly applied to any surface. If it's a surface that's perpendicular to the direction of propagation of that shock wave, then there is a significant magnification of the effects that are felt, the effective pressure on that surface. If it's parallel to the direction, or maybe on the backside of a building after it's washed over the whole building, or on the roof, so again, it's parallel, then you have what they call a free field pressure and impulse, and those values are a lot lower. So that's another mitigation strategy sometimes, is the orientation of your building to try to make sure that where you have close standoff, that one wall that faces maybe the one location where you're worried about is the one that's going to have to be beefed up a lot more than the other exterior surfaces of the building. Mm-hmm. So the pressure is that initial pressure, and then the impulse is the area under the pressure time curve. So that's where the milliseconds come into play. And in the real world, the pressure goes through an exponential decay back to ambient, again in a matter of milliseconds. And then there's actually a suction back toward the source of the explosion, although it's a much lower magnitude than that initial pressure. And it cycles a little bit back and forth back to ambient, again, within milliseconds. So it happens very quickly. The most common way to simplify that loading is, instead of an exponential decay, make it a linear decay. So your pressure impulse looks like a triangle. It's just a straight line from your maximum pressure at time 0 to 0 pressure at the equivalent duration. And what we typically do is we match the area under the curve. So the area under that triangle is the same as the area under the exponential decay of the more rigorous calculation of the pressure time curve.
So in seismic design, we learned something new, something we didn't anticipate, something we didn't notice. And it seems like every code cycle gets updated based on those items or those things that we learn. With blast design, are most of the new information coming out that are coming into the codes, are most of those more found by research, or do we actually go in and analyze buildings after there's been blasts?
Yeah, it's both. I think most of the research that's done in blast tends to be more to refine those response limits that we use to evaluate the behavior of a structure under a blast loading, so that we understand what appropriate, what value of ductility ratio and or support rotation corresponds to a somewhat more descriptive level of damage. Like I went through the 4 different levels of protection. And so that's where a lot of the more recent research has been done, because the equations that we use to model the loading have been around for decades. Those go back to research done around the time of World War II and things like that. And actually, a lot of work was done evaluating nuclear explosions. You've seen the videos, probably the black and white videos of the houses being disintegrated by a nuclear explosion. And so a lot of the equations came from research done during that time for that purpose, and then have been scaled down to more of the level of explosion that we're dealing with today, both in the anti-terrorism world and in petrochemical and some of the other fields. But that, it also is an important aspect of the industry that there are studies done when an explosion occurred. You mentioned 9/11. There was, of course, a study done to try to figure out why the Twin Towers in New York collapsed, and there is a canonical explanation of that based on that study, as well as the Pentagon. And what those ended up providing more input to the progressive collapse side of the industry as opposed to the blast resistance side, because it wasn't an explosion that was really the issue in those buildings. It was planes crashing into them and then fires raging uncontrolled for multiple hours. But I've mentioned Oklahoma City on a couple of occasions. ASCE did a complete forensic investigation of that event. And so I think a lot of our current knowledge about blast, and especially, again, progressive collapse, because that was a case where, because 3 columns failed, mainly due to shear because of the close proximity of the blast, something like 50% of the floor area of the building came down. It was a 9-story building with, it was designed before the 1983 continuity requirements for concrete design went into effect. So, it was kind of a house of cards once those 3 columns were removed. There wasn't the redundancy. There wasn't even nominal tying of the building together like you would have in a modern building. And incidentally, that may also turn out to be an issue with the condominium that collapsed in Miami recently, because that was built right before
79, right? Yeah.
It was under this. Yeah, it was built right before the 1983 code that introduced all those minimum structural integrity requirements. We'll see as that investigation goes forward. But just as they're doing an investigation to try to figure out what went wrong there, those have been done on cases where there were explosions at buildings. Now, they don't happen that often, at least not, again, in an anti-terrorism context. So we have the Oklahoma City bombing. There was a Khobar Towers bombing in Saudi Arabia in 1996 that drove a lot of the DoD criteria development for anti-terrorism design. There were the embassy bombings in the late 90s, 1998, I believe, in Africa. 3 different embassies were attacked, and that has really dictated a lot of the State Department requirements for this kind of work. So there is that forensic aspect of it, but again, a lot of the more recent stuff is based on things done in laboratories, doing shock tube testing, doing arena testing of explosives to try to refine our criteria, because we do have a fairly good understanding, we think, of what happens when an explosive goes off.
Yeah. What are the tools that are available if you go into this design? Are you using the same structural analysis software that we'd use for traditional design, or are there more specific programs that you might need?
It's really not feasible to use traditional structural engineering software because most of them are not set up for the type of dynamic analysis of an individual element that we do in blast design. Some of the more sophisticated programs can do dynamic analysis, and they're set up that way so you can use it for seismic. And there, again, in the petrochemical world, there might be ways to take advantage of that when you're worried about an entire building's response to a short duration or long duration, lesser magnitude type of blast loading. But in the anti-terrorism world, again, you're looking at a component by component basis. There are some tools out there that different companies have put together. A lot of them were originally funded by the government for their use, and a lot of them are still only available from the government and only if you have a contract where you have a need to use them for that purpose. So I've developed a spreadsheet that we use in-house that uses those simplified methods so that we're not reliant on anybody else's software, using that closed form equation that Newmark developed, which I mentioned earlier, to come up with the equivalent static loading and then doing the checks on what the connection capacities need to be and so forth. So there are ways to develop tools like that. There are a few out there that you can buy for prices that range from reasonable to unreasonable. And there are government programs, if you are doing that kind of work, that you can get permission to download and use for that purpose as well. one thing that can be a little more extensive, and we haven't talked about it yet, is glazing design for blast resistance. Structural engineers don't normally do any design of glazing systems. We just rely on the manufacturers. The architects write the spec. They might ask us for the wind load and things like that. It can be a little bit of a different story sometimes for glazing in a blast environment. And again, not so much that we have to design the entire system, but we just have to make sure, particularly where we're wanting to make sure we have an accurate cost estimate at the design phase. So we want to get an idea of, how thick does the glass need to be, and what kind of glass are we talking about? So normally in a blast resistant application, we're going to want to use laminated glass, and we're going to want that to be in the innermost pane of an insulated glazing system. And the idea there is that laminated glass will crack under a blast loading, but the laminate that's inside it will hold everything together, stick to those shards, and catch any fragments from the outer panes if those are not laminated and do fail. And there is software, again, both commercial and government software, to do that analysis and figure out, based on a given pane size, figuring out whether a certain thickness of laminated glass based on the outer layer and what layup that is and so forth. It'll do the analysis for you for a blast loading and figure out whether it's adequate. And it will also then give you a lot of times equivalent static loading that you use to design those perimeter members that we talked about earlier, whether it's cold form steel framing or masonry or concrete or structural steel in some cases, depending on the framing system for the building. So that is something that does sometimes add a little bit to our scope. But again, it's not typically a huge deal. Where we have very large curtain wall systems like you'd see on a courthouse these days, again, that's a job for a super expert, somebody who does curtain walls, blast design all the time, has their own specialized tools and techniques for doing that type of design.
So you kind of mentioned, with beam design, maybe you'd see some more bolts. And let's say you're reviewing a project that someone in your firm did. What would you be looking out for? What would you go, let's dive in a little deeper. It looks like you're maybe missing this.
Yeah, it's mostly for us. It's mostly just looking at the spreadsheet that I developed and looking at all the numbers, making sure they matched what was assumed, and probably having a conversation both beforehand and afterwards to make sure that the engineer understands the theory behind the spreadsheet. I've been developing the spreadsheet since 2001. I've been developing the documentation probably since about 2010, and it's still not done because it's one of those things that nobody's going to pay us for me to write documentation for our in-house software. But it's pretty close, and the theory part's all in there based on papers that I've written and things like that. So I think that's probably the most important thing, is just to make sure that an engineer understands the assumptions underlying a blast analysis and proceeds accordingly and doesn't do anything that would be unreasonable or unrealistic in the process of doing that.
One of the other things that is very simple that we like to ask, especially engineers with more experience, have been in the industry for longer times, what are certain things you see in a structural engineer that makes them good? What are you typically looking for, maybe when you're hiring somebody, or kind of the key things you see a good engineer does?
Yeah, the number one thing I pay attention to when we have a new grad or a younger engineer who's working under my supervision on a project is how often and what kind of questions do they ask? Because I stress all the time to all our engineers at all levels and in presentations and so forth, the most important thing for any engineer to know is what you don't know. Because we don't know everything. There's always uncertainty involved in anything that we do in the engineering world. That's why we have factors of safety. That's why we have these simplifying assumptions that we need to be aware of and make sure we're accounting for them with appropriate factors of safety and so forth. But the ones that I'm most comfortable with, if they're working for me on a project, are those who are coming to me fairly regularly with good questions. Again, there are no dumb questions in my opinion, so I stress to them, just ask, make sure that we're on the same page and that what you're doing is the way that I think is appropriate to be doing it. The ones I worry about are the ones who are quiet, that I don't hear from for a while. They're off working for a week or two and I'm like, well, what are you doing today? and then they have trouble even explaining what they've been doing over all that time. So that's what I would encourage younger engineers to do: is ask, ask, ask. Don't be shy. Don't be ashamed. Don't feel like you're making yourself look bad, because the better experienced engineers, which I hope I fall in that category, are going to be glad that you're asking and are going to be happy to answer those questions. Because in my experience, I don't remember what I didn't know 25 years ago when I was first starting. It all just sort of comes natural now because I've been doing it for so long. I've learned on the job, and it's instinctive. It's something that I'm exercising judgment rather than following a procedure that I've written out as a bunch of steps. And I do remember that as early in my career, you had to ask a lot more questions and make lots of lists like that and figure out, well, this is how you design a steel beam, and this is, and even some of the more creative stuff, this is how you lay out the framing for a roof of a particular shape where you can only have columns in these locations and things like that. And so a lot of times it's that kind of stuff where I'm like, oh yeah, you don't know how to do that yet, do you? And so we talk through it together, and I try to explain the reasons why I'm suggesting to do it a certain way, because they're not going to be obvious. There aren't going to be notes on the drawing that say, this is why the framing is laid out this way. This is why we're using a W16 member here, even though a W10 would have enough capacity, things like that. So again, it's really just about encouraging younger engineers to ask questions and always being willing and available to answer those questions, whatever they may be, and hopefully share the knowledge that we've accumulated over the years as they need to hear it. But I do tell them that I rely on them to ask the questions, because I'm not going to be able to know up front the 60 things we need to go over before they get started. I tend to have a 15-minute conversation and say, here's what needs to be done. When you have questions, come ask. Not if, when you have questions, come ask, and I'll be happy to walk you through the other parts.
But that was a great answer. Thank you very much.
Sure.
Yeah, I have my probably first level 0 engineer under me, and it is a good refresher of that you don't know anything. I mean,
yeah, it's a learning experience to work with a new grad.
Yeah,
that's what I found, because again, you come to realize and hopefully appreciate how much you didn't know back then.
Yeah.
And how much more you know now, not because you took a class or read a book or sat in a lecture, but because you just did it over the years and figured it out.
But thank you very much for all the information.
Yeah, my pleasure. It's been fun. Good conversation.
All right, you've made it. You're at the end. Thanks again for listening to the episode. Let us know if you have any questions by reaching out to us on LinkedIn, Facebook, Instagram, or email. You can find those links and more information about this specific episode in the show notes below. Have a great week.